Applications of exponential and logarithmic functions. In this lesson, we will look at the different applications of exponential and logarithmic functions. In particular, we will be looking at model for exponential growth and exponential decay, and then look at some problems involving logarithmic models, and then we'll choose an appropriate model for a data and express an exponential model in base E. In real-world applications, we need to model the behavior of a function. In mathematical modeling, we choose a familiar general function with properties that suggest it will model the real-world phenomenon we wish to analyze. In the case of rapid growth, we may choose the exponential growth function y equal to a sub 0 e to the kt, where this a sub 0 here is equal to the value of a at the time 0, or that's the initial condition. And the e here is the Euler's constant, and k is positive constant that determines the rate of or percentage of growth. We may use the exponential growth functions in applications involving doubling time. That is the time it takes for a quantity to double. Now, such phenomena as population, financial investments, biological samples, and natural resources may exhibit growth based on doubling time. Now, let's look at the exponential growth function more closely. This exponential growth function can be described by this graph here. The y-intercept is the point 0, a sub 0, or this point here is the initial condition. This is this a sub 0 here is the value of our a, or the y, the value of y, when t is equal to 0, and we call that value a sub 0. And since k is greater than 0, so this exponential growth function behaves as an exponential function, or an increasing exponential function. And also this function is a one-to-one function, and it has a horizontal asymptote at the line y equals 0, or the x-axis. And the domain for this function is the set of all real numbers. As you can see, you have graph on the x or the negative values of x, and you also have graph on the positive values of x. Now the range is the set of all positive numbers, or from 0 to positive infinity. As you notice by looking at the graph here, that this exponential growth function does not have a graph below the x-axis. And also, since we have the horizontal asymptote at the x-axis, or the line y equals 0, we could say that the graph here does not cross the x-axis. It's asymptotic to the x-axis. So therefore, we do not have an x-intercept for our exponential growth function. Now let us consider the following application problem. A research student is working with a culture of bacteria that grows at the rate expressed by the exponential equation given here. Take note that the time here, t, is in minutes. We want to answer the following questions. To the nearest whole number, what is the population size after 30 minutes? And then second, we want to find the time when the population will be 10 times its initial value, rounded to the nearest minute. Now, to answer the first question, it is important to understand the representation of this function. This f of t here represents the growth of the bacteria at a given time t, or that means the population or the number of bacteria at the given time t. So if you want to find the population size after 30 minutes, all you need to do is just evaluate this function here at t equal to 30, because t here is in minutes. So therefore, to get the population of the bacteria at t equal to 30, we will just plug in 30 to t. So we will evaluate this expression here, and plugging into your calculator, you get 3,341. That means there will be approximately 3,341 bacteria after 30 minutes. Now let me just illustrate how you will input or plug this into a Desmus calculator. This Desmus calculator will be available to you inside Pictorio during your test. So to evaluate 1,550 times E, so you just click 1,550, and then this is letter E, the Euler's number, raised to, so this is the function that you're going to click to raise to an exponent, so raised to 0.0256 times 30. So you just have to make sure that you write this or you plug it in according to the given function that you have. And as you can see, you will get here 3,340.949, and you round this off to the nearest whole number, you get 3,341. So that's how you get 3,341 bacteria after 30 minutes. So for the second problem, we want to find the time when the population will be 10 times its initial value, rounded to the nearest minute. So to answer this, when you say the population will be 10 times its initial value, we're referring to this 1,550 here. This 1,550 here is the initial value. So we're referring to 10 times of this value here. So we want to find the time when the population, when this f of t is equal to 10 times the number here. And so to answer that, we will just replace our f of t by 10 times 1,550, and that is equal to the right-hand side of the equation. So you just copy the right-hand side of the equation. Now notice that this 1,550 here is common on both sides. So we can divide both sides by 1,550 to cancel this number here on both sides of the equation. And that gives us 10 equal to e to the 0.0256t. Now since we want to compute for this time t here, we can take the ln of both sides. Since this exponential function is a one-to-one function, so we can do this. So getting the ln on both sides, we have ln t, or ln 10 is equal to, you know that ln e is just equal to 1. So if you have ln of e to the 0.0256t, that is just equal to 0.0256t. And then, since we want to take t, we can divide both sides of the equation by this number here, 0.0256t. So therefore, t is equal to ln 10 over 0.256, and that is approximately equal to 90. So we say that after 90 minutes, the population of bacteria will have reached 10 times its initial value. Next question. A biologist observed a population of bacteria that grew at the rate expressed by the exponential equation f of t equal to 358 e to the 0.0425t, where t is in minutes. We want to find how long will it take the population to reach 8 times its initial value. So in this problem here, we want to find the time for the population to reach 8 times its initial value. So that means that we are going to compute for t here when this f of t is equal to 8 times the initial value of the bacteria. The number here is the initial value of our expression. So to solve this, we're going to replace our f of t by 8 times 358. And so therefore, we solve this equation here. 8 times 358 equal to 358 e to the 0.0425t. Now, since 358 is common on both sides of the equation, we divide both sides by 358, so to cancel 358 on both sides. So therefore, we have 8 equal to e to the 0.0425t. And then we take the ln of both sides. We have ln 8 equal to the exponent here. So recall the property that ln of e to the t is just equal to t. So applying that property in here, ln of e to the 0.0425t is just equal to 0.0425t. Then, since we just want to solve for t, we want t, so we can divide both sides of the equation here by the coefficient of t. Therefore, t is equal to ln over 0.0425. And that is approximately equal to 49. So therefore, we conclude that after 49 minutes, the population of bacteria will have reached 8 times its initial value. Now, in the case of a real-world application where there is a rapid decay of a value, we choose to represent it with an exponential decay model of the form y equal to a sub 0 e to the kt, where a sub 0 here is the initial value. This is equal to the value of y at the time or when t is equal to 0. And this e here is the Euler's constant. Now, k here is a negative constant, and that determines the rate of decay. Oftentimes, we use this to calculate the half-life. The half-life is the time it takes for a substance to exponentially decay to half of its original quantity. We use half-lives in applications involving radioactive isotopes. An exponential decay have a graph that would look like this. As you see, it is a decreasing function, and the function would approach close to the x-axis, but it will not touch the x-axis. An exponential decay generally behaves like this. It is represented by the function y equal to a sub 0 e to the kt, where k is less than 0. That's why we have a graph that is decreasing. And the graph is also asymptotic to the x-axis. The line y is equal to 0. It will just approach the x-axis, but it will not cross it, or it will not touch it. That means we do not have an x-intercept for an exponential decay function, and the y-intercept is the point corresponds to 0 a sub 0, where a sub 0 is the initial condition, or the value of y when the time is equal to 0. And by looking at this, we see that the domain of an exponential decay function is the set of real numbers. We have graphs that on the corresponding to the negative values of x, and we also have a point on the graph of the function corresponding to the positive values of x. So that means that the domain of the function is the set of all real numbers. That is from negative infinity to positive infinity. And the range are only all positive y values. We do not have a graph below the x-axis, and the graph does not cross the x-axis. Therefore, our y values are values greater than 0. Now, one common term associated with exponential decay is the half-life. Half-life is the length of time it takes an exponential decaying quantity to decrease to its half, or to half of its original amount. So this is the time. So again, this is the time. When you say half-life, that is the time it takes for the function to decrease to half of its original amount. So to find the half-life of a function, we will just solve this equation here. We're going to replace our f of t by half of the value of a sub 0, and then we will calculate for our t, because we want to compute for the time for which f of t is equal to 1/2 of the initial condition. Now let's take a look at the following exercise. The half-life of carbon-14 is 5,730 years. Express the amount of carbon-14 remaining as a function of time t. Then determine how long it will take for the amount of carbon-14 to reach 40% of its original amount, rounded to the closest year. Now, to answer this, we are going to consider the function f of t equal to a sub 0 e to the kt. So we will set up the equation using the formula here. F of t is the amount of carbon-14, and a sub 0 is the initial condition, the value of the amount of carbon-14 at time t equals 0. And k here is the decay constant. Now notice that in here, we are given the half-life of carbon-14, which is equal to 5,730 years. So if you recall, half-life is the time it takes for this to reach half of its initial value. So that implies that at t equal to 5,730, our f of t is half of the initial value. So we have 1/2 of a sub 0 is equal to a sub 0 e to the k, and then the time is 5,730. Now, since we have a sub 0 on both sides of the equation, we can divide both sides by a sub 0. Then cancel that. Therefore, we have 1/2 equal to e to the k times 5,730. Now, we want k. We want to solve for k. So we can do that by taking the ln of both sides. And then we have now the ln of this, so ln of e to the 5,730k is just equal to 5,730k. Then we can divide both sides of the equation by 5,730. 5,730. That gives us k to be equal to ln of 1/2 over 5,730. Now, you can also apply the properties for logarithm here. You can write ln of 1/2 as ln1 minus ln2, and ln1 is equal to 0. So therefore, we have negative ln2 all over 5,730. So our k, this growth of decay constant, is equal to negative ln2 over 5,730. And so therefore, to get our function that describes the continuous decay, we're just going to replace the k here by the value that we got, that we have solved previously for k, which is equal to this expression here. So therefore we have f of t equal to a sub 0 e to the ln of 1/2 divided by 5,730 t. And then to answer the question, how long will it take for the amount of carbon-14 to reach 40 of its original amount rounded to the closest year, we're going to consider this function here and then replace f of t by 40% of a sub 0. So that is 0.4 a sub 0, and then you solve for t. So now we want to find t when f of t is equal to 0.4 times a sub 0. So you replace the f of t here by 0.4 of a sub 0. And then just copy the right-hand side expression. So we have this equation here, and we will solve for t. So first, we will divide both sides of the equation by a sub 0. And that a sub 0 cancels out. That gives us 0.4 equal to e to the expression here. Now we want t, and t is in the exponent. So we just take the ln of both sides. So taking the ln of both sides, we have ln of 0.4 equal to the expression here. And then to solve for t, we're just going to multiply both sides by the reciprocal of the coefficient of t here. So that is 5,730 divided by ln of 0.5. So you do that as well on the other side. So we have 5,730 divided by ln of 0.5. Now this would cancel with this and that. So therefore t is equal to 0.4 times 5,730 divided by ln of 0.5. Plugging this into your calculator, you get t equal to 7,575. Now let me show you how you will input that to the scientific calculator that will be available to you during your test. You can just write 5,730 divided by ln. So ln is here, so ln of 0.5, ln of 0.5, and then enclose that, and then times, you have to put the cursor here. Oops, you have to make sure you have that in the middle. Okay, so you have to put the cursor there using the arrow, and then times, you put ln of 0.4, and then enclose that. So you have here 7,574.647. Now you round this off to the nearest whole number. You have 7,575. Therefore, we say that it will take approximately 7,575 years for the amount of carbon-14 to reach 40% of its original levels. Also take note that to get the most accurate results, don't round until the last step of the problem. That means you don't get ln of 0.5 first, for instance, and then round it off to some decimal places. So you do the rounding on your last step. So you just input ln of 0.5 and ln of 0.4 in your calculation and do the rounding on your last step. Now let's consider another problem. Cesium-137 has a half-life of about 30 years. Given this half-life, we can represent its decay with the exponential decay function a equal to a sub 0 e to the ln of 0.5 divided by 30 times t. Now if we begin with a 400 milligram of cesium-137, how long will it take for the cesium to decay to the point where there is only 2 milligram remaining? Now in this problem here, we are already given this function here to represent the amount of cesium-137 at any time t. Now we will use this equation to solve for the question here. So since we are given 400 milligram of cesium-137 at the beginning, so our A sub 0 here is equal to 400. We want to compute for the time when the cesium will going to decay to the point where there is only 2 milligram remaining. So we want to compute for t when the amount is equal to 2 milligrams. So therefore we have 2 equal to 400 e to the expression here. Now to solve for t, we will first divide both sides of the equation here by 400. So dividing 2 by 400, we have 1 over 200. And then 400 divided by 400 is just 1. That's why we only have 1 here as the coefficient of our e. Then next, since we want t, we take the ln of both sides. So you take the ln of both sides of the equation here. And then you manipulate this by multiplying both sides by the reciprocal of the coefficient of t. So we have 30 because we only want t. So we want to cancel out the coefficient of t. So we have 30 over ln of 0.5. So that this would cancel this and that would cancel that. And you would also do the same thing on the other side. So you have 30 over ln of 0.5. And then that gives us t equal to the expression here. And this whole expression here is what you will use to input to your calculator to solve for t. That is also the same as dividing this expression here by the coefficient of t here, which actually what you see in here. So t, and then plug this into your calculator, gives you 229 years.